Friends, let me introduce myself. I am Ramaswamy Krishnan and I will be 80 years old in November 2024. I am an engineer by profession and an amateur mathematician. I have been working on a famous problem called FERMATS Last Theorem from the age of 20. Recently, I have found a proof for it, a very simple proof. This I have uploaded in Vixra.org, a website meant for amateur mathematicians. Under the heading, maybe Fermat's own proof. You can Google Vixra:2207.0016 and get the proof. This theorem has a dubious distinction of having the greatest number of false proofs. In view of this, I am making a $2,000 challenge. Anyone, the first person who is able to prove that my proof is also a false proof will get $2,000. They can contact me at my email ID ramasa421@gmail.com. Now about Fermat. Fermat is a very great mathematician of the 17th century. He is considered as the father of number theory, the present number theory, and he has contributed a lot to the theory of probability. In addition to that, he has done a lot of work on tangents, which is probably a forerunner to differential calculus of Newton and Leibniz. This theorem, after his death, his son, while going through a book, found on the margin of the book that he has written x to the power of n plus y to the power of n equal to z to the power of n has no solution in integers if n is greater than 2. And he has also written, he has found a good proof for it, which the margin is narrow to hold it. Now everyone knows that a squared plus b squared equal to c squared has got an integer solution starting from 3 squared plus 4 squared equal to 5 squared. Actually, the general solution for it is a squared minus b squared whole squared plus 2ab whole squared equal to a squared plus b squared whole squared. Now, if you put integer values for a and b, you will get all the infinite solutions. Now, this theorem became for a long time was unproved, and in the end, in 1995, Dr. Andrew Wiles proved it without proving it. Dr. Andrew Wiles proved that elliptical lines and cubical forms have one-to-one correspondence. This proof became a proof of Fermat's own theorem, Fermat's last theorem. Now, those who want to understand the proof, they can study Fermat's enigma by Simon Singh. This proof requires a lot of mathematical knowledge and is a very complicated proof. My proof is a very simple proof. This proof can be understood by all 11th and 12th standard students of India, but they require certain things to understand it, which is not taught in the 12th or 11th standard. How to work on reminders is taught only to undergraduate students of India and not for the 11th and 12th standard. So I am going to explain to them about 3 things. The first one is, if A, B and C are integers, then if I write A is congruent to B mod C or A minus B is congruent to 0 mod C, it means A minus B, if divided by C, will leave a remainder 0. Then second one is Fermat's own proof called Fermat's small theorem. It is a to the power of P is congruent to A mod P. There, if P is not a divisor of A, then then a to the power of p minus 1 is congruent to 1 mod p. This is a very important proof, and this proof I have used extensively here. Third one, if a is congruent to b divided by c mod p to the power of r, where p is a prime number and r is greater than or equal to 1, and c is congruent to 0 mod p to the power of s, it means AC is congruent to b mod p to the power of r plus s. So if you know all these things and understand it, you will be able to understand my proof. Now, to prove x to the power of n plus y to the power of n equal to z to the power of n has no solution in integers, you have to first prove it for 4. If you prove it for 4, all the multiples of 4, it gets proved. Fermat showed his own genius by proving for 4 by a method called infinite descent. Later, another great mathematician called Euler proved it for 3. Now what is required is to prove it for p greater than or equal to 3. If it is proved for all odd prime numbers, the theorem stands proved. Let us assume x to the power of p plus y to the power of p equal to z to the power of p, where x, y and z have no common factor and p is an odd prime number. Now that can be designed by this equation: z minus y plus y whole to the power of p minus y to the power of p equal to x to the power of p. This makes the z minus y a factor of x to the power of p, or p into z minus y a factor of x to the power of p. So if x is equal to p1 q1, we can write z minus y is equal to p1 to the power of p, and if x is equal to p to the power of alpha into p1 q1, we can write z minus y is equal to p to the power of p alpha minus 1 into p1 to the power of p. Similarly, for y is equal to p2 q2, z minus x is p2 to the power of p, and z is equal to p3 q3, x plus y is equal to p3 to the power of p. Let q be a prime factor of q1, that is q1 is congruent to 0 mod q. Now q minus 1 can be written as pk plus r, where r is less than p. Now because q is a factor of q1, q is also a factor of x, and therefore z to the power of p is congruent to y to the power of p mod q. That means z to the power of pk is congruent to y to the power of pk mod q. But according to Fermat's small theorem, z to the power of pk plus r is congruent to y to the power of pk plus r, each congruent to 1 mod q. This results in z to the power of r is congruent to y to the power of r mod q. Now r is not a divisor of p because p is a prime number and r is smaller than p. So what happens is the z to the power of p is congruent to y to the power of p mod q, and z to the power of r is congruent to y to the power of r mod q, results in r equal to 0. That is, q is congruent to 1 mod p. Hence, q1 is congruent to 1 mod p. Therefore, q1 to the power of p is congruent to 1 mod p squared. Similarly, q1 to the power of p is congruent to q2 to the power of p is congruent to q3 to the power of p is congruent to 1 mod p squared. Because q1 to the power of p is congruent to q2 to the power of p is congruent to q3 to the power of p is congruent to 1 mod p squared, we get from the fact that x to the power of p plus y to the power of p equal to z to the power of p, p1 to the power of p plus p2 to the power of p is congruent to p3 to the power of p. Now if you write z minus x plus z minus y minus x plus y, you will get x plus y minus z is congruent to 0 mod p squared. But if p is a divisor of z, say, then p1 into q1 to the power of p plus p2 into q2 to the power of p is congruent to p to the power of p alpha into p3 to the power of p into q3 to the power of p. Therefore, p1 plus p2 to the power of p is congruent to 0 mod p squared, because p alpha, even in the case of 3, is greater than 2. Then x plus y minus z is congruent to 0 mod p squared, and alpha is greater than or equal to 2. Hence x plus y minus z is congruent to 0 mod p to the power of alpha into p1, p2, p3. So x plus y minus z divided by p to the power of alpha into p1, p2, p3 is equal to p4. Then we can write x plus y minus z is equal to p to the power of alpha into p1, p2, p3, p4. But p4 will have no common factor with x, y or z because all the common factors are p1, p2, p3 and p alpha. Now the proof part 2 is let a is equal to x plus y, b equal to z minus y, c is equal to z minus x. If you do that, 2x plus y minus z is equal to a minus b minus c, and 2z is equal to a plus b plus c, and 2x is equal to a plus b minus c, and 2y is equal to a minus b plus c. Therefore, 2 to the power of p into p to the power of alpha into p2 to the power of p3 to the power of p into p4 to the power of p will be equal to 2x plus y minus z whole to the power of p. So I am going to add a 0 to the right hand side. That 0 is plus 2z whole to the power of p minus 2x whole to the power of p minus 2y whole to the power of p. This means a minus b plus c whole to the power of p plus a plus b plus c whole to the power of p minus a minus a plus b minus c whole to the power of p minus a minus b minus c whole to the power of p. This once work out, it comes to 4abc into sigma 1 to p minus 1 to b of pc2r into a to the power of p to the power of p minus 2r minus 1. Then start another bracket 0 to r minus 1 of 2r into c to the power of 2s plus 1 into b to the power of 2r minus 2s minus 2 into c to the power of 2s. In continuation of part 2, the equation that is derived is for 3, if p is a 3, it works out to 2 cubed into 3abc. Now, the equation is balanced for 3 because if 3 is a divisor of x, y or z and p4 is equal to 1, then the equation is completely balanced. But for p to the power of p is equal to 5, then the LHS is equal to 2 cubed into 5 abc into a square plus b square plus c square. Now what you have to understand is, of the numbers x plus y minus z, x, y and z, x plus y minus z is the smallest one. And p4 is you divide x plus y minus z by p to the power of alpha into p1, p2, p3, you get p4. So p4 is a very small number, and this shows that RHS is greater than LHS. And if you go one step higher, p4, it becomes much more bigger than LHS. But it has to be proved. And part 3 of the proof is the proof of the point that p is a divisor of x, y or z and p4 is equal to 1. Proof part 3. Let x and z be two positive integers with no common factor, and z minus x is less than x is less than z. This means y is the smallest of the three, and let y to the power of p is equal to z to the power of p minus x to the power of p. Now it is clear that y to the power of p is an integer because x and z are integers. Now assumption 1, y is an integer. If I take y as an integer, then I can apply FERMATS small theorem. That is y to the power of p minus 1 is congruent to 1 mod p. So it becomes y is congruent to z minus x mod p. If y is congruent to z minus x mod p, y to the power of p is congruent to z minus x whole to the power of p mod p squared. Therefore, z to the power of p minus x to the power of p minus z minus x whole to the power of p is congruent to 0 mod p squared. Assumption 2. P is not a factor of x, z or z minus x. If p is not a factor of z minus x, I can divide by p. So a is equal to z minus x minus z minus x whole to the power of p divided by z minus x whole to the power of p is congruent to 0 mod p squared. For convenience, I am taking another term p. P is equal to a divided by p is congruent to 0 mod p. But as y is congruent to z minus x mod p, y by z minus x is congruent to 1 mod p, or we can write y by z minus x equal to 1 plus k1 p. Now it will be continued in the next page. So we can write y divided by z minus x is equal to 1 plus k1 p. Now taking a raised to the power of p, y to the power of p by z minus x whole to the power of p is equal to 1 plus p into k1p plus pc2 into k1p squared, etc. That means z minus x, z to the power of p minus x to the power of p by z minus x whole to the power of p minus 1 is equal to p into k1p mod p cubed. Therefore, p into k1p is congruent to a mod p cubed. So k1p is congruent to a by p mod p squared, or is congruent to b mod p squared. Therefore, we can write 1 plus y by z minus x is equal to 1 plus b plus k2p squared. Again, raising to the power z to the power of p minus x to the power of p by z minus x whole to the power of p is equal to 1 plus b whole to the power of p plus p into k2p squared into 1 plus b whole to the power of p minus 1 plus so on. That means 1 plus pb plus p into p minus 1b squared plus p into k2p squared mod p to the power of 4. So dividing by p, this is minus 1 is a by p is equal to b plus p minus 1 into p squared plus k2p squared. Therefore, here this is b is equal to a by p, they get cancelled. So k2p squared is congruent to 1 minus pb squared. Therefore, y by z minus x is equal to 1 plus b plus 1 minus p by b squared plus k3p cubed. It goes on like this. So we can write y minus z minus x is 1 plus b plus 1 minus p by 2 factorial b squared plus k3p cubed. This can be continued, which resulted y by z minus x is equal to 0 to infinity of 1 over pcr into a to the power of r. But a is greater than 1, therefore y tends to mod y tends to infinity. Hence our assumption 2 is wrong, and p is a divisor of x, y or z. Now we go to the assumption 3. The assumption 3 is p4 is greater than 1. Now if p4 is greater than 1, it must have a prime factor. Let that prime factor be q. If q is not a divisor of x, and q is not a divisor of x, z or z minus x, we can write y is equal to z minus x 1 plus m1q. Continuing the process done for p, again mod y tends to infinity. Therefore, p4 is equal to 1. If p4 is equal to 1, the equation under part 2 gets modified as 2 to the power of p into p to the power of p alpha minus 1 into p1 to the power of p into p2 to the power of p into p3 to the power of p into p is equal to 4 abc into p into 1 over p into pc2r. This p will be get divided by this p, so there is no problem. Now this entire thing, p into p, ABC, because p is a divisor of a, b or c, ABC is equal to p to the power of p alpha minus 1 into p1 to the power of p into p2 to the power of p into p3 to the power of p. Then this p is there. So they get cancelled, if we can cancel it. The 2 to the power of p is equal to sigma that comes, and 4 into sigma that comes. So this is obvious that RHS is greater than LHS. So the equation is not balanced actually. So the equation to get balanced, the division should not be possible. If the division is not possible, that is possible only if z is one of ABC is 0, that is z is equal to x. Therefore, x to the power of p plus 0 to the power of p is equal to z to the power of p is the only solution. That FERMATS theorem is proved for p greater than or equal to 5. The mathematicians are under 3 assumptions. Assumption 1 being that Fermat's theorem cannot have a simple proof. But it has. Assumption 2 is, amateur mathematician like me cannot prove Fermat's theorem. The assumption 3 they make is that if a proof of Fermat's theorem is submitted, it has to be a false proof. Now I do not agree with those things, and hence I have declared that anyone who is able to prove that this is a false proof, or the first person who tries to prove that this is a false proof, will get $2,000. That is my $2,000 challenge. That's all, my friends. Thank you very much for watching it.